I didn't realize you had joined. My headphones weren't picking up anything for a bit.
Well, excuse me. Yeah. We had some things to do this week. This week, we, of course, missed class on Monday because of the holiday. I always forget about the holiday. And so we have to try to rearrange things a little bit. We are starting with our first chapter of honest to goodness physics this week, chapter 3. We will go through this chapter as if we're going to be able to complete it this week. We'll see if we actually can. If not, we'll push off till next week, but we shall see about that. I don't know if I actually populated anything in our quizzes for this section. Let's take a look here. No, I didn't populate anything in them. We will go ahead and just not have a quiz today. I will go ahead and erase that one later on here. We will just get into things because we're going to be busy trying to catch things up today anyway. So before we move into chapter 3, first, which is one-dimensional motion, does anybody have any final questions from chapter 2? Seems like I didn't get any requests for help during the weekend, so I'm assuming everybody did okay working through the last of homework chapter 2 on vectors. Hopefully that is the case. If you're still having some questions, don't hesitate to contact me. I want to be able to help you out with the things that you are needing help with, but we will go ahead and move on to chapter 3 today, which is our first chapter of physics in one dimension. We're going to go through a lot of definitions today, and we're going to learn about the kinematic equations. We're going to do some examples of calculating things using the kinematic equations. Hopefully we'll get to that today. That might take us till Friday to get to, but we'll go through some stuff and then turn you loose on the homework. So we're going to start with the definition of position. In order to describe where something is, we need to have some system for describing it in. This is what we call a coordinate system, right? And in order to have a coordinate system, we need to have an origin, the place that we measure from. And then we need to have coordinates. The coordinates are usually in what do we call a Cartesian coordinate system. Cartesian is named for Descartes, French philosopher and mathematician. And he came up with this idea of having coordinates that were 90 degrees from each other. And the reason that they're 90 degrees from each other is so that they're independent of each other, right? If you're moving in the X direction, you're not moving in the Y direction. If you're only moving in X, you're not moving in Y, and vice versa. You can be moving in both dimensions if you're moving between the two axes, for example. But if you're only moving in one of them, you're not moving in the other one, and that makes them independent. That turns out to be quite important, especially when we get into two-dimension stuff. In one dimension, you're essentially traveling along a line, forward and backward along a straight line. That's one-dimensional motion. So if we're doing a coordinate system with one dimension, we just have a line. One point on the line is considered 0, but we also have to consider which way is going to be positive, which way is going to be negative. Since we read from left to right in the English language, we generally choose to the right of our 0 point to be positive and to the left to be negative. It doesn't have to be that way. It's just the way we usually do it. And then you've got your coordinate system defined. If you're defining a coordinate system on paper, you should draw it. And I would recommend drawing it using arrows. So if this is my one-dimensional coordinate system here, I would use a line with an arrow on one end. The arrow represents the positive direction. The other direction is negative. And then you choose a point on this line to be your 0 point. Maybe it's right here. Just label that 0 and you're good to go. There's your coordinate system. You can call it the X coordinate system if you want, in which case you might put an X over here to show that that is the positive X direction. But it's important to label all these things, the direction of the coordinate system, the actual coordinate system itself, the direction using an arrow so you know which way is positive, and the origin. And then of course label your coordinate. This one is being labeled X. Position will be defined in any coordinate system from the origin toward a position. So let's say that we have a position of 6 in this coordinate system. We might represent that using a vector that goes from the origin out to 6, like that. And position can be represented as a vector. It can also just be represented as a coordinate, +6. But for the case of our definitions, we will actually define position as a vector. You could also have a position of -3. -3 would actually be half as long as the 6 and in the opposite direction. And position vectors always start from the origin and go out to the point of the position. Position vectors are the only vectors that must start at the origin. All other vectors can start wherever they need to start in the coordinate system. And then we move on to the next definition, which is displacement. When you move from one point to another point in a coordinate system, then displacement is the vector that goes from the beginning point to the end point, right? So here's a teacher in front of some kind of whiteboard or something like this. And she's going to go through a displacement where she starts at x naught at 1.5 meters. That's her initial position. Her final position is 3.5 meters. And her displacement vector, which goes from her initial position to her final position, is going to be 2 meters of displacement. And the definition for that mathematically is you take the final position and you subtract the initial position. So we take the 3.5, subtract the 1.5, and we get 2. Now this formula takes into account the sign of the direction of the displacement. If you're plugging in your positions with the correct signs, plugging them into this formula will give you a displacement with the correct sign, in other words. And displacement is also considered a vector. Here we're representing it as a vector. They're not writing it as a vector in this equation. And if they were, they might boldface this or put an arrow over the top or both. But it should be a vector. It is a vector. It does point from the beginning point towards the ending point. In this case, it points in the positive x direction. If you have many displacements that you're going to add, that you want to add together to get a total displacement, that's simply it's simply done. You can actually add all those vectors together one after the other to get the total displacement, or you can just take the final position of the final displacement and subtract the initial position from the first displacement, and you get the total displacement. Either way, it works out here. Now moving on from displacement, we have position, now we have displacement. Moving on to, actually before we move on, we need to talk about the difference between displacement and distance. Displacement is not the distance unless you want to consider it to be the straight line distance between 2 points. But even then, displacement is not exactly just the straight line distance, because displacement is a vector and it does include direction. Distance is not a vector, and distance does not include the direction that you take, and distance is not always the straight line distance between 2 points. The distance usually be used to describe how far someone actually traveled along whatever path they took. An example of this would be, traveling between here and Kearney, for example. To travel from North Platte to Kearney, it's about 100 miles. And if you're traveling along I-80, that is true, that your distance traveled would be about 100 miles. And it's a fairly straight line path between here and Kearney. It's not perfect, but it's, somewhat straightish. However, you can get to Kearney all kinds of different ways. You can go to McCook first and then travel to Kearney. And that's obviously going to take more than 100 miles, and it's obviously not going to be in a straight line. McCook is south from here and Kearney is east from here, right? You could travel to Broken Bow and then to Kearney. And then you'd be going a completely different way again and a completely different distance again. It's the distance traveled depends on the path that you take. The displacement between 2 points is always the same. It never changes depending on the path that you take. Now we move on to average velocity. So average velocity between 2 points is defined very simply as the displacement between those 2 points divided by the time needed to go through that displacement. Not necessarily the time needed. I think that's a bad way to say this. It's the time taken, not the time needed. It's the time that it actually required to go between the 2 points. And so the average velocity is an average, and the reason it's an average is because you're measuring something at one time, you're measuring something at another time, and you really don't know what happened in between those 2 times. You didn't take any measurements in between. So you have to assume that everything in between happened, uniformly. And by making that assumption, you're calculating an average. Why would that be an average? Well, imagine that you're driving between here and Kearney. If you're taking my truck might be able to travel 100 miles an hour, so I might be able to take that trip in an hour. It's really pushing it to get it to 100 miles an hour, I would guess, but it might be able to hit it. So if I took my truck and I get to Kearney in an hour, you can pretty much be guaranteed that I was traveling 100 miles an hour the whole way, because it's the only way I'm getting there in an hour, is to just flat out all the way 100 miles an hour the whole time. However, if we're driving my dad's car, my dad has some kind of fancy BMW with pipes coming out of the side kind of car. It's like a race car roadster thing. And it has a speedometer that goes up to like 170 miles an hour or something like this, 160 miles an hour. And so you could take his car and you could drive to Cozad and stop and have lunch. I don't know if there's any place in Cozad for having lunch, but you could stop somewhere along the way and have lunch, stop wherever you want to stop. And then you could drive the rest of the way and still be there in an hour. And the only times you would actually be driving 100 is when you blew through it on the way, speeding up, and when you pass through it, slowing down when you got there, right? You would never actually be traveling 100 miles an hour, because you'd be traveling faster than that most of the time to make up for the fact that you stopped for lunch. But your average would still be the same if it took you an hour to get there, because all we know is that you started in North Platte, and then an hour later we saw you in Kearney, because those are the only 2 places we measured. So we have to assume that you were going 100 miles an hour the whole way, or we just say that we calculated an average, which is the same thing. So that's why average velocity, whenever you're measuring things between 2 different times, you're always measuring some kind of an average. And even when you're calculating the speed when your car is calculating the speed while you're driving, it's taking averages. That's all it's doing, taking averages. It takes them much more rapidly than most measuring people do, but anyway. So here we have an example where we're going to do some calculating of some things here from these formulas. Also, the average velocity is also a vector because displacement is a vector. So if displacement is a vector and you divide the displacement by the time to get velocity, that means velocity is also a vector. And if your displacement is positive, your velocity will also be positive for that same amount of displacement during that displacement. So your average velocity will follow along with that. So here we have Jill sets out from her home, delivering flyers at a yard sale, traveling due east, lined with houses. At 0.5 kilometers, 9 minutes later, she runs out of flyers, retraces her steps back to her house. So she's going back 0.5 kilometers, takes an additional 9 minutes, picking up more flyers. She sets out again, same path, ends up 1 kilometer from her house. Third leg takes her 15 minutes. At this point, she turns back toward her house, heading west. After 1.75 kilometers in 25 minutes, she stops to rest. So what is Jill's total displacement to the point where she stops to rest? So this is just back and forth movement, right? We have east and we have west. We're going to consider east to be our positive, west to be our negative. And this is what happens. She goes 0.5 kilometers away from her house, then back. Then she goes 1 kilometer away, and then she goes back. But on her way, when she's going back to her house the last time, she actually goes 1.7 kilometers backwards or in the negative direction, which means she actually ends up beyond her house. So her final position is actually 0.75 kilometers to the left of her house. Now, if we consider her house to be 0, then she ends up at negative 0.75 kilometers. And she started at 0, right? So if we want to know part A, what's Jill's total displacement to the point where she stops to rest? Well, where's her resting point here? That was at the very end, I believe, right? Yeah. So her stopping to rest point is way over here. And she starts essentially here. She starts along this line and goes to here. So that one we just answered by doing the very simple math, but we could easily do it using the formula, which is the final position minus the initial position. That gives us her displacement. We calculated the final position to be negative 0.75, and we calculated the initial, or we figured the initial position to be 0. And that would give us a final position or a displacement of, it would give us a total displacement of negative 0.75. They actually do it a slightly different way. They just add together all of the displacements. So the 0.5 displacement, then the negative 0.5 displacement, then the 1 displacement, then the negative 1.75 displacement, and then you add them all together and you get negative 0.75 kilometers displacement. That works also either way. In part B, they want to know the magnitude of the total displacement. So the magnitude of negative 0.75 is just 7.75 because that's what magnitude does, takes the negative sign off of it. Then they want to know the average velocity. Well, the average velocity, you take this displacement, which is the negative 0.75, and divide it by the time. Go back and add up all the minutes that it takes for her to do all these things, time. So like all the way to 58 minutes to do this. And that's the time, right? Now, how do we want to calculate it in this problem? We probably want to do here they go ahead and calculate kilometers per minute, I guess. And that's fine, I suppose. Turns out to be negative 0.013 kilometers per minute. May want to convert that into meters per second, which means you'd have to use the kilometers to meters conversion and then the minutes to seconds conversion. Make sure you do that right. And then they want to know the distance traveled. Well, distance and displacement are different, remember. Distance is how far you actually travel, And in this case, it's 5 kilometers, then another 5 kilometers. You're essentially adding up all of these displacements as absolute values. So you take the absolute value of these displacements, add them all up, and you'll get a total displacement, which in this case, not a total displacement, a total distance. In this case, you add them all up and you get 3.75 kilometers. Now, the thing that really tends to bug people when it comes to displacement and distance is what happens when you walk away from somewhere and go and do your thing, and then you come back to where you started. What is the displacement if you end where you began? It is a 0 displacement, right? So displacement of somebody who goes to New York City and then comes back home, their total displacement is 0, right? Because their final position and initial position are the same position, same number minus same number always equals 0. However, the distance traveled is a very different thing. That depends on where you went and how you went there, right? So that's the thing that can really confuse people, is the displacements of 0. Then they go ahead and have us graph Jill's position as a function of time. So she goes out to 0.5. She does that in 9 minutes. And then she comes back to her home, takes another 9 minutes. So we're out to 18 at this point. Then she goes on this longer trip back out again, twice as far out. And then she comes back even further than her house. And so all you really need to do to create a graph like this is create the positions at each timestamp. At 9 minutes, 0.5. At 18 minutes, 0 again. At whatever time this is, looks like 32, 33-ish minutes. She's out at the 1 kilometer mark. And then after all the time has elapsed, she's 0.75 meters past her house in the other direction, kilometers rather. So you can just plot those points and connect the dots. Yeah. So that gives us position, displacement, distance, average velocity. And that is, that's a good start. That helps us to get started on this stuff. However, because we are taking this class that is a calculus-based class, we need to understand how calculus plays a role in doing some of this work. And that's going to have to do with instantaneous velocity. There is a way to actually calculate the instantaneous velocity of an object from a, for example, if you know the functional form of its velocity that it's taking. So if you know that it's in a gravitational field, you know the functional form of a gravitational field, then you can use the functional form, and it's going to be some kind of function. It's going to be a quadratic function. And you can use that function to actually calculate how fast they're going at any given time. Instead of an average from between this time and this time, you could actually say at this time, at this moment, how fast is it going if you have some kind of function that describes its velocity. And this is very important to modeling the physical behavior of the universe. And that's something that we do as scientists and engineers. So something to understand about, something we definitely want to understand about. Now, if you've taken calculus already, then you'll recognize this. If you're just taking calculus for the first time, I'm not sure if you're here yet, but you might be getting close to this, should be. But the idea of the derivative comes into play here, right? Haven't gotten to the derivative yet? Well, the idea of getting to limits is the idea of derivatives. So. Yeah.
I didn't take the test like pass out.
That's all right. Well, we're going to teach you about derivatives here anyway. And you're going to learn different things about derivatives here than you will in a math class for the most part. in your math classes, you're going to spend a lot of time going through the theory and the limits and all these things, and that's fine. There's nothing wrong with learning that. It's important to understand kind of the underpinnings of calculus. But mostly what we're going to teach you is what these things do and how to use them. For most physicists, mathematics is like a hammer. You know, it's a tool, it's a screwdriver. It's something that we use to get something done. And the theory of how a hammer works is not as important to most physicists and engineers as just learning how to use the hammer itself, right? The theory is important. There's no question that it's important. I think it's ironic that physicists and engineers think this way. I think engineers think more this way than physicists do, but it's ironic that physicists think this way because we invented calculus. So we should have a great understanding of the theoretical underpinnings of calculus. And I honestly think that physicists have the best understanding of calculus. I don't think that anybody understands calculus better than physicists in general, because we did invent it for this purpose. We invented it to calculate things like instantaneous velocity. It was invented by Newton, in fact. And there are some people that would debate that. Some people that would argue that there are, especially German people tend to debate this because there were two brothers, the Leibniz brothers, that discovered calculus at about the same time Newton did. But it's obvious from the historical record that Newton actually did discover it first. And not only did he discover it first, he discovered the uses of it before the Leibniz brothers did by far. The Leibniz brothers mostly kind of just developed a way of writing it down. It's what they're most famous for. But anyway, so what is a derivative? And this is the big deal here. This is what mathematicians like to write down when they say, what is a derivative? Right? So they write this down, and most people look at this and say, what is this? Well, what this really means, if we look at this, what this limit does here is this limit is looking at two positions of something. Here's the first position, x at time t. So this tells us the position at time t. And then it looks at it at some other position, time t plus delta t, where delta t is a tiny extra bit of time. So this is a little bit later. This is the position at the first time you look at it. This is the position a little bit later, or the final time that you look at it. So here we have final position minus initial position, and then you divide by that little change in time there. And then you take this limit, you essentially squeeze that time down to a very, very tiny little bit of time, so that the two positions you're looking at are essentially right next to each other in time. And that limit allows us to look at two times that are extremely close together or infinitely close together, and to zero in on that displacement over time, or that velocity at that point in time, right? And we use this notation to represent what's going on over here. And it turns out that calculating the derivatives of mathematical functions is not terribly difficult. There are some patterns that we can use to help us to remember how these things work out. But anytime you see a derivative, you see this dx dt or dy dt or something here. Anytime you see a derivative, what that derivative is doing is it's looking at the function. In this case, our function is x, and it's looking at it in terms of the variable t in this case. So the dt on the bottom tells us what part of this function it's looking at. And the derivative looks at the function and determines how the function is changing with respect to that variable. So this one is looking at x and seeing how it's changing with respect to time. So when you take this derivative of this function, you'll get some answer, and that answer will tell you how that function is changing as time goes by. Okay? And it could be another function, it could be a constant, and it could also be zero. Those are the three things that come out of a derivative. You either get another function that tells you how this function will change in time. So that means that the changing of the function is actually changing as well. If you get out a constant, if you do take a derivative of something, you get like 5, then you know that you're going to have a very specific constant change, 5, right? And then if you get 0, that means there will be no change. That means the function that you're looking at and that you're taking the derivative of has no change in time, and it's going to be the same all the time. Whatever it started at, that's what it will be later. So that's what happens if you get a 0 out from a derivative. No matter what the function, all functions have a derivative, all of them. Some of them have multiple derivatives, but all functions have derivatives. It doesn't have to be a derivative in time. It often is when we're dealing with physics, but it doesn't have to be. You can also look at how a function changes in space and changes with respect to other variables. So derivatives are quite versatile. But the instantaneous velocity is defined as the time derivative, d by dt, of the position function of time. So that means if you're given some kind of function with time in it that says, you know, that's supposed to be the position of a particle in time, then you can take the time derivative of that function, and that will tell you the instantaneous velocity function. And if that's also a function in time, then you can plug in a time and calculate the velocity at some particular point in time using the evaluation of that function. And we're going to go ahead and do some of that. Well, this is an example of it. This slope, this curve right here, kind of looks like an upside down parabola or something. This could represent the position of a particle. In fact, it would be a fairly good representation of a particle in projectile motion, like like kicking a soccer ball or something like this, punting a football or something. So you've kicked it, and now only gravity is acting on it. And as gravity acts on it, actually slows it down in the y direction, slows it down in the upward direction. And then it gets to the top where it's at its highest peak, and then gravity starts to pull it downward and speed up again. So that's a fairly good representation of something like kicking a football. And you can see we have all these different representations of slopes between points on the line, on the curve. We have the point between this point and this point, between this point and this point, and this point and this point. All 3 of these bottom lines, the orange, green, and purple, represent average velocities between 2 points in time of this ball or whatever it is that's traveling through the air. But the one on the top is different because it is actually measuring the slope of the top of this graph essentially, but it's only using 1 point right in the middle. This one, the purple one's using 2 points on either side of the curve, green one's using 2 points, red one's using 2 points. But this one at the top, this blue one here, is only using 1 point. And that's because what they've done is they've used that limit to bring those 2 points closer and closer and closer together until they become 1 point. And whenever you take the tangent line, put the tangent line slope on a function like this, that slope of that line will tell you the instantaneous velocity. So at this point, at the peak of this thing, the slope of this this line at the top that is actually tangent to this point on the curve is about 0. So you know that once it gets to the top of its motion, it hits about 0 velocity. And anything that stops and turns around and comes back has to hit 0 velocity at the top of the motion. So that makes sense. And this derivative is also measuring the slope of the function. So because it's measuring the change of the function, that the change of a function is also considered its slope. So if you're looking at a position versus time graph like this, the instantaneous velocity at any given point will actually be the slope at any given point. So you can actually just calculate the slope of this graph and call that the velocity. So right here we have this slope that's very constant. It's nice and linear. It's staying at a constant positive slope all the way. Let's calculate the slope. Looks like it's going to be about, so we're taking rise over run. The rise is about 0.5. over the run, which is about 0.5 as well. So 0.5 over 0.5, it looks like. Yeah, so that's about 1. So we have a slope of about 1.5 over 0.5 between time 0 and time 0.5. Right, we get about 0.5 over 0.5, so it's about 1. And then all the way between 0.5 and 10 or 1 second, then it's nice and flat here, and that's a slope of 0. And then at the end, we start up here at 0.5, we go all the way down to 0 again. So we have a rise of negative 0.5 as it goes back down to 0. And we're going all the way from 10 to 20. So that happens in essentially, or not 10, but 1 to 2 seconds, 1 to 2 seconds. So that happens in about 1 second. In 1 second, we go from 0.5 all the way down to 0. And that's going to be a change in velocity over that time period of negative 0.5 over 1. So we have 0.5 over 0.5, which is 1 for the slope here, negative 0.5 over 1 over here, which is going to be negative 0.5 for our slope at the end. And that's what we get. We get a 1 meter per second slope at the beginning. We get 0 at the top when it's just flat lining and the slope is 0 at the top. So at that flat point, we have 0 meters per second, not moving at all. And then on the way back down, it's going it's going back down at this constant slope of negative 0.5 meters per second for the full second. And if you want to graph those velocities, then it's 1 between 0 and 0.5. And between 0.5 and 1, it's 0. And between 1 and 2, it's at negative 0.5. And there's your velocity graph. Notice here that they put some dotted lines connecting here and here, and that's because those are not part of the graph. That's just to help us recognize that the graph does go on. All right, so speed. We've talked about position, displacement, distance, average velocity, instantaneous velocity. Now speed. Well, speed is similar to distance. It's not something that cares about direction. Speed is just about how fast am I going right now, right? So, or whatever. So we can calculate average speed, but it's not going to consider direction, not going to take direction into account. And it is going to take distance into account. So how far you actually traveled on the path that you took matters when it comes to speed. So if I travel from here to McCook to Kearney, it matters that I travel from here to McCook and then from McCook to Kearney. All the distance matters. It's going to change my average speed calculation. But you essentially take the total distance traveled divided by the time it takes to travel that distance, you get the average speed. And it is a scalar quantity, just like distance is a scalar quantity. No direction involved. It's just how fast you go. The instantaneous speed is actually going to be considered the absolute value of the velocity at that given time. So that can be a very different thing. If it's asking for instantaneous speed, you have to calculate the velocity vector, take its absolute value to get that. Now we move on to the good stuff. Calculating instantaneous velocity using a derivative operator. How do we actually do a derivative? Well, we're going to use derivatives primarily with polynomials, because polynomials are often used to model physical behavior in the natural world. You can model just about any function using a polynomial of some kind. And so this is how we do a derivative of a polynomial in t. The independent variable in our function will be time t, and this looks a little bit I don't know, mysterious or something like this. A n t n minus 1, all this stuff, d by dt, whatever. But it's easier to see when we have just a real example. So here's an example of a polynomial. X of t equals 3 meters per second times t plus 0.5 meters per second cubed times t cubed. Right? This is a polynomial function that is representing the position of a particle. In some way, is it a simple particle position? No, it's not simple at all, but that's not outside the realm of possibilities to have complex particles, particle behavior. But what this equation tells us is it tells us where the particle is at any time. So if you want to know where the particle is at 4 seconds, then you just plug in t equals 4 here. So you're going to get 3 times 4, which is going to be 12, and then you're going to add to that 0.5 times 4 cubed. Well, 4 cubed is 64, so you have to multiply this 0.5 times 64 and add it to the 12 over here that you're going to get, and so on. And that's what this function does. You plug in different times, you get different positions for the particle. However, if you want to know the velocity, then you take the derivative of this function, and then you plug in times, and that will tell you the different velocities at different places in time. So here's the calculation of that velocity function. We take the derivative of this function with respect to t, and this formula back here tells us how to do it. You have a derivative of some number times t raised to some number. And when you have that happening, the first thing you want to do is you want to realize that the constant in front of the function, constant in front of the t, just kind of pulls through the derivative. The derivative does nothing to that. So it comes through and it's still there, a. But then you're left with d by dt of t to the n. The a has come out in front, and you're left with something else. So let's actually write this out so you can see what it looks like. So the first step is we bring the a through. The a comes out. Any multiplier constant in front of your polynomial stuff can come out, but it has to come out term by term, not all of them at once. So this a can come out, and what we're left with is d by dt, derivative in time of t to the n power, right? D by dt of t to the n with a out in front. This part is the part where we're going to use a pattern from doing these things. There's a set pattern that comes out when we do the limits. And you'll learn about this more in calculus if you don't know it yet. But this pattern for polynomials, or your variable raised to some number n here, is that the number in the exponent comes down in front of the t. So you end up with this equaling a. You bring down this n and it comes out n. And then you put your t back in the equation, and then your n back in the equation up here, and then you subtract 1 from the n. And that's the pattern for the derivative of a polynomial term. Now we do this term by term. If you have multiple terms added together, then you can split it up and do each term separately, and then add all the answers together at the end. But that only works when you're adding them together. If they're multiplied things together, then it changes things a bit. So let's take a look down below of how we do this here. Here we have two terms. We have 3 meters per second t, and we have 0.5 meters per second cubed t cubed. Two different terms. We're going to treat them differently when we do this. We're going to use the derivative to calculate a velocity function, right? Here's our position function. We take the first one, which I'm going to do up here, I guess. So we take the first term and do its derivative first. I'm going to get rid of the meters per second just because it's going to make it easier. We're just going to end up with 3 times t. So we want to do the derivative d by dt. And this, well, anyway, that's just good. Then that's 3 meters per second times t. Okay. So we've got the 3 times t in the end, d by dt. We've gotten rid of the units just to make it cleaner. So how do we do this derivative? Well, the first thing we do is we pull out the constant. The constant comes out in front. So we end up with 3 d by dt of t. Now, this t here is actually, it does actually have an exponent. What is the exponent of a t? It's a 1, right? So we're going to go ahead and use that 1 and do the next part of our derivative. We're going to actually do the derivative. So 3, and we're going to bring down the 1 times 1, and then we're going to multiply by what's in here again times t, right? 3 times 1 times t. But now we take our n, which was the 1, because the n was the number that was started off in here, which is a 1. So we're going to take that 1 and we're going to subtract 1 from it. But 1 minus 1 is, of course, 0, and t to the 0 is equal to 1. So this whole thing becomes just 1. And we end up with 3 times 1 times 1, which is just 3. And this always happens when you have a derivative with respect to a variable of just the variable. So d by dt of t is always just 1. And if you take d by dt of 3t, you're going to end up with just 3, because 3 is a constant that came. So that's our first one. The first part of this, part of this function here, the derivative of the first part actually is just a 3. So our new function d by dt of x of t, that's the derivative we're doing, which is also the same as v of t, right? We've done the first term, and the first term is equal to 3. Now we do the second term. The second term is this one here, and I'm going to take out this unit stuff here, and it's going to equal 0.5 t cubed. So if I do d by dt of 0.5 t cubed, I do the same thing again. I pull the constant through, the constant comes out front, that's 0.5. And then I'm left with d by dt of t cubed. Remember, it's the same thing. You bring down the number that's up here in the top, bring it out, and you bring it out in front. So that's 3 times 0.5. And then you rewrite the function with that number in it again, minus 1. So 3 minus 1. Simplify this, and it becomes 3 times 0.5 is 1.5. And then the t to the 3 minus 1 is t squared. So there's our second term derivative. That goes down here. We're adding, and the sign goes with it, so you have to make sure these signs come through. So this one is plus 1.5 times t. So this is a whole new function here, but this will tell us the velocity at any given point in time. If I want to know the velocity at 5 seconds, then I plug in 5 for t here, and I get 3 plus 1.5 times 5, which is 7.5, and that would be equal to 10.5. So after 5 seconds, its velocity is 10.5 meters per second. That is the idea behind this stuff. Now we're out of time for today, but we are going to move on to another lab for this week, and I will. So we did lab 1. We're going to move on to lab 2 for this week. So make sure that you get working on that. and the homework as well. Hopefully, we'll see how the homework goes and how we get through all the chapter. We might end up pushing into next week, but we'll see how that goes on Friday. So we'll see you Friday. Have a good day.
Oh, wait, can I didn't get all of homework 2 finished. I was wondering if you could move it forward to like tomorrow, at least. Just
Yes, I can do that.
thank you. Sorry about that.
No worries.
Also, the lab, yeah, I see you're looking at the labs right now. Or experiment 3 is due at the end of the night tonight, and experiment 2 is due Saturday.
Fix that. All right. See you later.
You have a good day.
You too.